Most engineers are tasked to solve problems, but in a Louisiana workshop, one engineer was given a different task: to solve a monster. His blueprint was a helicopter engine, and his goal was to cage it inside a motorcycle frame. The component was a Rolls-Royce Allison 250 turbine, an engine designed to lift a 2-ton helicopter. By the rules of physics, this was impossible, but they built it anyway. Here's how a Louisiana marine company built the most insane street-legal vehicle ever created, and why it nearly killed the people brave enough to ride it. Ted McIntyre's fascination with turbine engines began in childhood, while watching military jets screech across Louisiana's skies. While other kids collected baseball cards, McIntyre sketched turbine designs and dreamed of unlimited power. By the 1990s, his company Marine Turbine Technologies had become America's premier specialist in adapting aircraft turbines for civilian use. They'd stuffed jet engines into speedboats that could outrun Coast Guard cutters. They'd built industrial generators that could power small towns. They'd even experimented with turbine-powered cars that could theoretically hit 300 miles per hour. But McIntyre had a problem. Success was boring him to death. His marine turbines were making MTT wealthy, but they weren't making headlines. Industrial applications were profitable but invisible. McIntyre wanted to build something that would force the world to notice turbine technology's true potential. He needed a platform that would showcase raw power in its most dramatic form, something that would make people stop and stare, something that had never been attempted before. The motorcycle industry in 1999 was exploding with innovation. Suzuki's new Hayabusa was making 173 horsepower and hitting 195 miles per hour. Honda's CBR 1100XX Super Blackbird was pushing similar numbers. Manufacturers were locked in a horsepower war that was driving technology forward faster than ever. McIntyre looked at this arms race and saw an opportunity. Instead of building a motorcycle engine, he'd use an engine that wasn't meant for motorcycles at all. The question that would change everything was deceptively simple. What would happen if you put a helicopter engine in a motorcycle? The Rolls-Royce Allison 250 series wasn't just any helicopter engine. It was the turboshaft that had powered American aviation for decades. Bell helicopters, Hughes aircraft, military transports. This engine had lifted tons of cargoes, carried troops into combat, and operated in conditions that would destroy conventional motors. The 250 C18 variant that McIntyre selected produced 420 shaft horsepower in aircraft applications, but motorcycles don't use shaft horsepower the same way helicopters do. The conversion process would be brutal, complex, and potentially deadly. Aircraft turbines operate in a completely different environment than ground vehicles. They're designed for constant altitude, steady airspeeds, and cooling airflow that motorcycles could never provide. Adapting one for street use required solving problems that had never existed. How do you cool a turbine designed for 150 miles per hour airflow when the motorcycle is sitting in traffic? How do you manage fuel flow when the engine was designed to run at constant RPM? How do you deal with heat that could literally cook the rider? McIntyre knew these challenges would require expertise that MTT didn't possess. He needed someone who understood both aircraft engineering and motorcycle dynamics, someone crazy enough to think the project was possible. That was when he found Christian Trevert. Christian Trevert wasn't your typical motorcycle designer. He'd built custom bikes that looked like they belong in science fiction movies. Machines with radical geometries, exotic materials, and performance that pushed legal boundaries. But Trevert had never worked with turbine engines. No one had. The project would require inventing solutions for problems that didn't have names yet. The first challenge was basic physics. Aircraft turbines spin at 52,000 RPM. Motorcycle transmissions are designed for engines that redline at 12,000 RPM. Connecting these systems required gear reduction so extreme it was almost comical. The turbine's power curve was equally problematic. Piston engines build power gradually across their RPM range. Turbines produce maximum torque almost instantly, then maintain it across their entire operating range. This created power delivery unlike anything motorcycle riders had experienced. Heat management became the project's biggest nightmare. The turbine's exhaust temperature reached 1200 degrees Fahrenheit. That's hot enough to melt aluminum and start fires. Traditional motorcycle cooling systems were completely inadequate. Trevert's solution was radical. Instead of trying to cool the turbine, he'd isolate it. The engine bay became a heat-shielded chamber that protected the rider while allowing the turbine to operate at aircraft temperatures. The fuel system required complete rethinking. Aircraft turbines are designed to burn kerosene-based jet fuel, but street-legal vehicles needed to use commonly available fuels. Trevert discovered that the turbine could burn almost anything combustible, from diesel to high-proof alcohol. After 3 years of development, testing, and refinement, the first Y2K prototype was ready for its maiden ride. Nobody knew if it would work, explode, or just simply refuse to move, but they were about to find out. The first Y2K test ride took place on a closed runway in Louisiana. Christian Trevert climbed aboard a machine that had never been ridden, powered by technology that had never been used this way. The startup sequence was borrowed directly from aviation checklists. Fuel pumps activated, computer systems initialized. The turbine began its slow spool up from 0 to idle speed. The process took several minutes and sounded like a helicopter preparing for takeoff, because that's exactly what it was. Once the turbine reached operating temperature, Trevert engaged the transmission and rolled forward. The bike moved slowly, almost silently except for the banshee shriek of the turbine. Power delivery was unlike anything he'd experienced. There was no clutch to feather, no gears to shift, just continuous building thrust that seemed to have no upper limit. The bike accelerated like it was being pushed by an invisible hand that grew stronger with speed. By the end of that first ride, Trevert knew they'd created something that would change motorcycling forever. The Y2K wasn't just fast, it was a completely different kind of machine that happened to have 2 wheels. But creating the prototype was only the beginning. Turning it into a production motorcycle would require solving an entirely new set of problems. Building the first Y2K was engineering. Building 20 of them was a logistics hell. Every component had to be custom manufactured because nothing from existing motorcycle supply chains could handle the requirements. The frame needed to be constructed from aerospace-grade aluminum to manage the heat and stress. The transmission required special materials to handle 52,000 RPM input speeds. Even seemingly simple components became complex. The exhaust system couldn't use traditional motorcycle mufflers because they'd melt instantly. The cooling system needed aircraft-grade heat exchangers. The electrical system required military specification wiring that could operate in extreme temperatures. Sourcing the turbine engines became its own challenge. Rolls-Royce didn't sell new turbines to motorcycle manufacturers. MTT had to purchase used engines from aircraft salvage yards, then completely rebuild them to motorcycle specifications. Each engine cost between $60,000 and $80,000 before modifications. The rebuilding process took months and required specialized knowledge that only a handful of technicians possessed. Every engine was essentially custom built for its specific motorcycle. The certification process was equally complex. The Y2K needed to meet street legal requirements in multiple countries while using technology the regulators had never encountered. Emissions testing, noise regulations, safety standards, everything had to be negotiated case by case. Quality control became obsessive. MTT couldn't afford recalls or warranty failures with such expensive machines. Every component was tested beyond normal motorcycle standards. Every system was verified multiple times before delivery. The result was a production process that resembled building fighter jets more than manufacturing motorcycles. Nothing prepared people for the Y2K sound signature. Traditional motorcycles rumble, roar, or scream depending on their engine configuration. The Y2K created something entirely different. At idle, the turbine produced a high-pitched whine that could be heard from blocks away. It was the sound of something spinning incredibly fast under enormous pressure, something that sounded like it belonged on an airport tarmac, not on a suburban street. Under acceleration, the sound became genuinely frightening. The turbine's whine rose to a banshee shriek that reached 130 decibels. That's jet engine loud, construction site loud, hearing damage loud if you weren't wearing protection. The sound wasn't just loud, it was alien. People who had heard the Y2K approaching couldn't immediately identify what they were hearing. The brain processed it as some kind of aircraft, not a ground vehicle. This created problems that MTT hadn't anticipated. Noise complaints from neighbors became routine. Track days required special sound restrictions because the Y2K could exceed noise limits just by idling. Some racing venues banned turbine-powered vehicles entirely. The psychological impact was more dramatic. The sound triggered fight-or-flight responses in people who weren't expecting it. Pedestrians would dive for cover thinking an aircraft was crashing nearby. But for riders, the sound became addictive. Nothing else on the road could produce that spine-tingling shriek of pure power under stress. It was the sound of physics being pushed to its absolute limits. The Y2K's exhaust system produced temperatures that redefined what motorcycles could generate. At 1200 degrees Fahrenheit, the exhaust was hot enough to cause third-degree burns in seconds. But the heat wasn't limited to the exhaust pipes. The entire rear section of the motorcycle became a heat source that could cause serious injury. Riders had to be careful where they placed their legs, arms, or any body part that might contact heated surfaces. The bike's cooling system was a marvel of engineering that barely kept the machine from destroying itself. Heat shields, thermal barriers, and specialized cooling circuits worked constantly to manage temperatures that would melt conventional motorcycle components. Parking became a legitimate safety concern. The Y2K could start grass fires, melt plastic car parts, or cause burns to anyone who touched the wrong surfaces after a ride. Owners had to plan where they parked as carefully as they planned their routes. The thermal mass of the turbine meant that heat continued radiating long after the engine was shut down. The cooling down process could take 30 minutes or more, during which the bike remained dangerously hot to touch. Some owners reported that the heat signature was visible on infrared cameras hours after riding. The Y2K didn't just run hot, it became a mobile heat source that required constant respect and caution. The Y2K's fuel flexibility was both a blessing and a curse. The turbine could burn almost any combustible liquid, which meant riders weren't limited to premium gasoline or racing fuel. Diesel fuel worked perfectly and was available everywhere. Kerosene produced excellent power and was relatively inexpensive. Jet fuel, when available, provided optimal performance but was difficult to source legally. But the real surprise was how well the turbine ran on alcohol. High-proof vodka, rum, even medical-grade ethanol could power the machine in emergency situations. Christian Trevert famously demonstrated this by running a Y2K on tequila during a promotional event. The 9-gallon fuel tank seemed large until owners discovered the Y2K's appetite for fuel. Under normal riding conditions, the bike consumed fuel at rates between 5 and 10 miles per gallon. Aggressive riding could drain the tank in less than an hour. Gas station visits became educational experiences. Attendants who weren't familiar with turbine engines would ask endless questions about the bike's unusual sound, smell, and appearance. Some refused to believe it was actually a motorcycle. The smell was distinctively different from gasoline-powered bikes. Diesel fuel created a heavy industrial odor. Kerosene produced a sharp, almost medical smell. Whatever fuel the Y2K burned, it announced its presence long before anyone saw the machine itself. Jay Leno's ownership of a Y2K transformed the bike from exotic curiosity into genuine celebrity vehicle. His famous description of the riding experience, like the hand of God pushing you in the back, became the definitive explanation of turbine-powered acceleration. But Leno wasn't the only celebrity drawn to the Y2K's extreme nature. The bike attracted owners who collected the most exotic, powerful, and unusual vehicles ever built. These weren't casual motorcycle enthusiasts, they were people who measured success by how many laws of physics they could break in a single vehicle. Each owner had to undergo extensive training before taking delivery. MTT required proof of riding experience, insurance coverage, and mechanical understanding of turbine systems. This wasn't a bike you could buy and figure out later. The learning curve was steep and unforgiving. Turbine engines responded differently to throttle input than piston engines. There's a noticeable lag when the turbines spool up, followed by a surge of power that could catch inexperienced riders off guard. Unlike conventional motorcycles where riders could feel engine behavior through vibration and sound changes, the Y2K ran so smoothly that traditional feedback was absent. Riders had to learn to read different signals: exhaust heat, turbine pitch, transmission behavior. The complete lack of vibration was described by riders as eerie or unsettling. Motorcycles are supposed to vibrate, make noise, and provide tactile feedback. The Y2K smoothness felt unnatural to riders accustomed to conventional bikes. Most owners discovered that the Y2K demanded complete mental focus. This wasn't a motorcycle you could ride while thinking about other things. Every ride required concentration and respect for the machine's extreme capabilities. Independent testing of the Y2K's performance capabilities proved that MTT's claims weren't marketing hyperbole. The bike could actually achieve the speeds and acceleration numbers that sounded impossible on paper. Cycle World magazine's testing recorded a quarter-mile time of 9.8 seconds with a trap speed of 141 miles per hour. These numbers were competitive with purpose-built drag racing motorcycles, achieved by a street-legal machine with full lighting, turn signals, and license plate mounts. The top speed testing was more challenging because few facilities could safely accommodate a motorcycle capable of exceeding 200 miles per hour. The official record of 227 miles per hour was achieved on a closed runway under carefully controlled conditions. But riders who had access to longer test tracks reported speeds approaching 250 miles per hour before running out of nerve or runway. The Y2K's theoretical top speed was limited more by aerodynamics and rider courage than engine capability. The acceleration characteristics were unlike anything testers had experienced. Instead of the typical motorcycle power curve that builds gradually through the RPM range, the Y2K delivered continuous acceleration that felt more like being launched than driven. 0 to 60 miles per hour times consistently measured under 2.5 seconds, but the most impressive number was 60 to 120 miles per hour, which the Y2K could accomplish in less than 3 seconds. This was acceleration territory that few automobiles could match. The bike's high-speed stability was surprisingly good despite its unconventional power source. The long 68-inch wheelbase helped maintain control at speeds where other motorcycles became unmanageable. The Y2K's handling was a study in contradictions. Despite weighing 460 pounds and measuring 68 inches between wheel centers, the bike was surprisingly manageable at moderate speeds. The long wheelbase that made high-speed stability possible created challenges in tight corners. The Y2K required more effort to change direction than conventional sports bikes, feeling more like a touring bike than a performance machine. But the smooth power delivery eliminated many of the handling problems associated with high-performance motorcycles. There was no abrupt power surges to upset chassis balance, no engine vibration to cause handling instability. The suspension components were top-shelf Öhlins units that could be adjusted for different riding conditions, but the bike's weight distribution was unusual because the turbine engine was much smaller and lighter than equivalent piston engines. Braking performance was exceptional, partly because the massive Brembo brake system was designed for the bike's extreme speeds, but also because turbine engines provide virtually no engine braking. Riders had to use the brakes for all deceleration. The complete absence of engine braking felt strange to riders accustomed to conventional motorcycles. Rolling off the throttle didn't slow the bike significantly, requiring constant brake input in situations where other bikes would naturally decelerate. Cornering clearance was generous because the bike's smooth power delivery didn't require aggressive lean angles to maintain speed through turns. The Y2K was faster in a straight line than through corners, which matched its intended purpose. MTT's development of the Y2K didn't end with the original production run. Each bike built incorporated improvements and refinements learned from previous machines. The 2006 Street Fighter version increased power output to 420 horsepower using a more advanced Rolls-Royce 250 C20B turbine engine. This represented a 31% power increase over the original design, achieved through better fuel management and turbine optimization. The 2015 420RR incorporated modern electronics, improved aerodynamics, and enhanced cooling systems. Carbon fiber bodywork reduced weight while providing better heat insulation. Advanced engine management systems improved fuel efficiency and performance. But each evolution came with higher costs and complexity. The 420RR's price approached $200,000, putting it in competition with exotic automobiles rather than motorcycles. Production numbers remained intentionally low because MTT couldn't achieve economics of scale with such specialized manufacturing. Each bike was essentially a custom build that shared some components with previous machines. The company also developed a 3-wheeled version for customers who wanted turbine power with improved stability. The trike configuration solved some of the handling problems while maintaining the dramatic visual and auditory impact. But MTT's ultimate achievement wasn't building faster or more powerful versions. It was proving that turbine technology could work in motorcycle applications and creating a new category of exotic vehicles that had never existed before. The Y2K's influence extended far beyond its tiny production numbers. It proved that small, specialized manufacturers could push technology boundaries in ways that large corporations wouldn't attempt. The bike's success inspired other exotic motorcycle projects that explored unconventional power sources and extreme performance capabilities. While none matched the Y2K's turbine power, many borrowed its philosophy of ignoring conventional limitations. MTT's manufacturing process influenced how other exotic vehicle manufacturers approached small batch production. The combination of aerospace-grade components, custom manufacturing, and individual customer specification became a template for ultra-exotic vehicles. The Y2K also demonstrated that there was a market for vehicles that prioritized absolute performance over practical considerations. This encouraged other manufacturers to develop increasingly extreme machines for wealthy enthusiasts. But perhaps the Y2K's most important legacy was proving that the impossible was merely difficult. Ted McIntyre's simple answer, because nobody had done it before, became a philosophy that inspired engineers and designers across multiple industries. The bike showed that innovation often comes from outside established industry boundaries. MTT wasn't a motorcycle manufacturer, which allowed them to approach motorcycle design without preconceived limitations. The Y2K remains the only street-legal turbine-powered motorcycle ever mass-produced. It established performance records that still stand today and created a category of vehicles that continues to inspire extreme engineering projects. 25 years after its introduction, the Y2K still represents the absolute pinnacle of motorcycle performance. No production bike has matched its power output, top speed capability, or sheer audacity of concept. The few surviving examples command prices that exceed their original cost, making them not just performance machines, but investment-grade collectibles. They represent a moment in automotive history when someone decided that normal rules didn't apply. It goes without saying that the MTT Y2K could melt asphalt with its exhaust while screaming towards 250 miles per hour. Would you have been brave enough to ride it? Let us know in the comments what you think about pushing technology beyond all reasonable limits, and if you want more videos about the machines that shouldn't exist but do anyway, hit that subscribe button and prepare for more engineering insanity.